In this section I'm going to talk about carbon capture and storage, and this is the only way, well, in the short to medium term at least, that we're going to meet our self-imposed targets for reducing the amount of carbon dioxide in the atmosphere, and that, as I say, is to capture it and store it and not release it into the atmosphere. So what is CCS? Well, kind of talked about it briefly in the past section, but here's a good definition from the Intergovernmental Panel on Climate Change, and it is carbon, and often the dioxide is kind of dropped. So carbon capture and storage is a process consisting of the separation of carbon dioxide from industrial and energy related sources, transport to a storage location, and long-term isolation from the atmosphere. Okay, so essentially that's what you're trying to do. And there are three parts to this problem. There's the capture of the carbon itself, so the carbon capture, the storage of that carbon dioxide, and that has some obviously quite stringent requirements, and the transportation between the two. And this shouldn't be underestimated, although I'm not going to talk about this in this section. I'm going to focus on the carbon capture and the storage. But the transportation is quite important, because obviously where you capture it isn't necessarily where you're going to be storing it, so you need to get it from A to B, and doing that has its own challenges, whether you transport it down a pipeline or in tankers or whatever. It has its own challenges, but as I said, I'm not going to talk about that in this section. So how do we actually capture the carbon dioxide without releasing it into the atmosphere? So there's a number of ways that we can do this, and I'm going to talk about these in turn. So there's pre-combustion, post-combustion, oxy-fuel combustion, and also direct air capture, which is not involved in any combustion. So post-combustion capture, I'll talk about this one first. So this is kind of fairly intuitive. So what we've got is we've got a standard plant. So air and fuel are burnt in the boiler here. Air and fuel are burnt, that generates steam in the boiler. That steam is then used to turn a steam turbine, which generates electricity. Now the flue gases from the boiler, they're first passed through a sulfur dioxide scrubber. That's normal practice. That'd be done to prevent that being from released into the atmosphere. But the additional thing here is that after the CO2 scrubber, the flue gas is passed through what's called a carbon dioxide absorber. Okay, and in the CO2 absorber we have this amine solution. Okay, and the amine solution, when it's relatively cold, will absorb the carbon dioxide, and so it'll bond with it, so it'll take it out of the flue gas. And this amine solution is basically on a cycle. So in the absorber, it absorbs the carbon dioxide solvent, as I just said, and that's then passed into this stripper or regenerator. And by using a little bit of the steam that we're generating for our steam turbine, if we send that into our regenerator, we can warm the amine solution, and by heating it, it releases the carbon dioxide. So we just have carbon dioxide here. That's we can deal with that. We can now that's been captured, or well, it's been isolated. So now we can capture it and store it elsewhere. And then the solvent, which is now being freed from its carbon dioxide, can be cooled and passed back into the absorber, where it absorbs more carbon dioxide, and around it goes. So the second one is pre-combustion capture. So unlike the other one, instead of capturing the carbon dioxide after the combustion process, we're capturing the carbon dioxide before the combustion process. So the way that this works is air is brought into a separation unit where the nitrogen and oxygen in the air are separated. Then the oxygen from the air is passed into what's called a gasifier, and in here the oxygen is reacted with the fuel around kind of 700 degrees C, something like that. And so the fuel isn't burnt. That's quite an important point to make. The fuel isn't burnt, rather it's just reacted with the oxygen. And what that does is it creates a syngas, which is composed of mainly hydrogen, carbon dioxide and carbon dioxide. And so you've created this syngas, this synthetic gas. And that then is passed into what's called a shift reactor. And by using some steam from your process, you can convert the remaining carbon monoxide into carbon dioxide. And that can be separated from the hydrogen. So in here, we're just removing the carbon dioxide from your syngas. So you can see here now, this has obviously been isolated and now captured. So we haven't burnt anything. We've just basically taken our hydrocarbon fuel and we've converted it into carbon dioxide and hydrogen without burning it. We can take the CO2 and isolate and store that as we would from any other process. The hydrogen then is then used as our fuel. So we can put that into a gas turbine and burn that to generate electricity. We'll obviously have a flue gas, but because hydrogen is the only reactant going into here, it doesn't have any carbon. So our flue gas will just be water, okay? Because that's all that we're getting. Hydrogen plus oxygen gives you water. And then to improve the efficiency of our system, we could, because this flue gas is coming out at a high temperature from our gas turbine, we can recover some of that heat to generate more steam to then drive an additional turbine, this time a steam turbine, to generate more electricity. So we're using the fuel twice. We're burning the fuel to generate electricity. We're then recovering heat from the exhaust to generate steam to drive another turbine to generate electricity. Okay. So I said all that. Okay. So this is kind of an evolution of the pre-combustion technology. And so in the same way, the air and the air is split into nitrogen and oxygen. But this time, instead of gasifying the fuel, we actually burn the fuel. So the fuel is burnt in the presence of oxygen, but because it's burnt only in the presence of oxygen, there's no nitrogen in there, so we can't end up with any NOx or anything funny like that. So we burn the fuel in the presence of oxygen. That generates steam, which we drive our steam turbine. But because it's, as I say, burnt only with oxygen, our flue gas is purer in the sense that we don't have any NOx or anything like that, but we should just end up with carbon dioxide and water. Okay, and because we only end up with carbon dioxide and water, we can pass that into a condenser where we can easily separate the water from the carbon dioxide, say just by condensing the water out, and then that gives us a source of carbon dioxide, which is we can readily then isolate and store. Okay, so lastly, this is direct air capture, and as I said, this doesn't involve any combustion. This is quite a new technology, but you know, there's demo plants being developed, and companies are investing in this. And the idea is that these units are kind of I mean, they're big, but they're relatively small in terms of industrial plant equipment. So they're small enough that you can plonk one of these things on the top of a building, or maybe to have an array of them on top of a building. And the idea is that they just literally capture the carbon dioxide from the air. So a fan draws in the air, which has the carbon dioxide in, and it passes it over this substrate, which is porous, and it has a filter which is treated with amines. And if you remember, we mentioned that in the post combustion technology, that was the solvent that we used to absorb the carbon dioxide. So again, it's being used here, and the so the substrate adsorbs into the filter. Okay, that's not absorb. So adsorb is just onto the surface, not an absorb is actually into the volume. So it just absorbs onto the filter, and then the CO2 lean air is passed out the back. And so it does this for a while till its sensors tells it that it's captured, until the amine solution has been saturated with carbon dioxide. Then it shuts down the fans, and what it does is, in the same way that with the post-combustion capture we regenerated the solvent, it does the same thing here. So it heats the filter, the CO2 is released, and then so it's now been isolated, it's captured and stored. So it heats the filter up, removes the carbon dioxide, and then once it's cooled down again, it can go round and around on the cycle. So that and then the idea then is you can have a network of these across the rooftops of a city, all just busily capturing CO2 out of the air. So one thing that should be said here, so we talked obviously about how we can capture carbon dioxide from our combustion systems, whether that's pre-combustion or post-combustion, and but really the amount that we're being captured isn't what we should be talking about, and I'll illustrate that with an example. So let's say this is our reference plant without carbon capture and storage technology fitted. So it'd be producing this amount of carbon dioxide, let's say. Now, with our plant with CCS, now the technology we have is pretty good. We can extract between 85 and 95% of the carbon dioxide from the flue gases, which is great. However, the technology requires energy to work, and it requires around 10 to 40% more energy. So you can see illustrated here, the plant with CCS is producing more carbon dioxide than you would have for your reference plant, but it is capturing, as I say, 85 to 95% of that. So what you really want to be talking about is the carbon dioxide avoided. So this is what's captured, the amount here, but what's actually been avoided is this much, because if you hadn't done anything, this is how much carbon dioxide you would have had, and this is how much you got left over. So it's that CO2 avoidance, which is what you're really interested in. So I talked about carbon capture, so I'm now going to kind of focus on storage. And there's kind of three main ways of doing this. There's geological storage, ocean storage, and mineral carbonisation. And again, I'll talk about each of these in turn. So geological storage, this is pretty well established technology. So we have oil and gas wells, and the way that these are obviously natural phenomena. These are naturally occurring places where we could easily store carbon dioxide, because the characteristics of an oil or gas well is that it has this very dense, what's called catwalk, which has trapped the oil and gas underneath it. So it's perfect if it can trap methane gas for millions of years, then there's no reason why it shouldn't trap CO2 for millions of years if we do it right. So we're using these natural oil reserve to actually use for geological storage of carbon dioxide. So, and actually the technology exists. So the idea is you pump carbon dioxide into the ground to store here, and the oil and gas companies are actually doing this already. The reason they're doing it, not necessarily because they care about the environment, but because they've realised that by pumping carbon dioxide into the oil reserve, you can increase the pressure of your in your reservoir, and that improves your productivity of your refinery because you can extract more oil from the ground. And this is called enhanced oil recovery. And as I say, they're already doing this. So we have the technology to do this. We've got a perfect storage location in the depleted well. So this seems like a good way to go. And according to the Climate Change Committee, this is very likely to exceed. Sorry, the retained fraction is very likely to exceed 99% over 100 years, and likely to exceed 99% over 1,000 years. So you can see it's a very safe and stable way of storing carbon dioxide. Another way that's been discussed, which I have to say I'm less convinced about, is what's called ocean storage. Water will naturally absorb carbon dioxide, and so the ocean is a large body of water. So the idea is that you could dissolve carbon dioxide into the ocean, and that would act as a storage mechanism. And there's a couple of ways that you could do this. You could either kind of pump it in fairly deep, around 200-300 meters, I think, and as it wouldn't bubble up as I've kind of illustrated here, but as you release it at those depths, as it rises to the surface, it would naturally absorb into the ocean anyway. The other way is that if you pump in the liquid carbon dioxide into very deep parts of the ocean, then actually the pressure of the water column of water above the carbon dioxide would keep the carbon dioxide liquefied on the seabed and kind of just store it there. Obviously that's quite risky. If there's any shift in the tectonic plates at the ocean bed, you could risk suddenly releasing a large amount of carbon dioxide into the atmosphere. On top of that, if you increase the concentration of the carbon dioxide in the water, you're making it more acidic, you're reducing its pH. So this increase in acidity is, as I say, one of the reasons I think this isn't perhaps the way to go. That's just my opinion. But because the biologists are already concerned about the pHs of the oceans decreasing, or the acidity increasing, just because from the natural absorption of the carbon dioxide from the atmosphere into the water without additionally pumping tons of it into the ocean as well. So the effect on marine systems need to be very carefully considered if this is an approach that's going to be taken forward, at fairly large scales. Last one, mineral carbonisation. Now this is a good option in the sense that what it effectively is that you store the carbon dioxide chemically by bonding it with a metal. So rather than just kind of storing it in a chamber or dissolving it in a liquid, it is bonded, so it would be very, very stable. Once you'd locked that carbon dioxide in with those metal oxides, it wouldn't come out, not without a lot of process. And this is a natural process. CO2 in the rainwater is dissolved. The carbon dioxide dissolved in the rainwater bonds into the rocks as it filters through, and this is a process that, say, occurs naturally. It just takes a long time, millions and millions of years. But this process can be sped up by pre-treating the minerals and using high pressure carbon dioxide. Obviously that requires a huge amount of energy. So this technology is very immature currently, or to scale it up, there's not the carbon dioxide saving that you'd want. So what you're storing, or the mineral carbonisation, isn't storing as much carbon dioxide as you're producing from compressing it from the process. So it's good, and then there's no chance of leakage, but as I say, at this stage it's very energy intensive and not viable for scaling up at this moment in time. So all of these technologies have a cost. I've already talked about the carbon capture requiring some additional plant, which has an additional energy cost. So I'm not going to go through this slide in detail, but you can see that capture from a coal or gas-fired power plant is $15 to $75 per ton of carbon dioxide. And whereas direct air capture, that's kind of, hundreds of dollars, but this price is expected to reduce or even halve in the second generation of technology. Mineral carbonisation is very expensive in terms of storing compared to comparing to capturing from power plants. Sorry, something I should have said here, there's a bit of a price range on here. And whether you're using post-combustion capture or pre-combustion capture is going to impact on the price. The advantage of post-combustion capture is that can be retrofitted to any power plant or process that we have now. You could just tack that on the end. However, with a pre-combustion capture technology, although the yield and the efficiencies might be higher, you have to have that upfront investment. You can't easily retrofit that technology onto an existing plant. It's better to incorporate into a new plant that you're building from scratch. So there's pros and cons, obviously, to each of these technologies and the costs that's associated with them.